This slide details a couple of things that are important. Equivalent protons don't split each other. So hydrogens on the same carbon generally don't split each other because they're considered to be equivalent. They're not always equivalent, but if they are equivalent, they won't split each other. Protons on adjacent carbons generally will split with one another. Protons separated by four more bonds will not. So for example, if I have this type of hydrogen and this type of hydrogen, that would be considered long-range coupling, and we don't normally see that except, and I think I mentioned an exception at some point. What is the exception?
Aromatic rings.
Aromatic rings. We do see this effect a little bit. Here's an example of ordinary splitting. This is ethyl benzene. And ethyl benzene has typical, and these multiplets here are not expanded, but I've got a quartet here and a triplet here. And you remember the n+1 rule. And so these guys up here, the CH2 here is going to be split by 3 hydrogens next door. That's what's going to create the quartet. The 3 hydrogens here are split by 2 hydrogens next door, which is what creates the triplet. We see 5 hydrogens according to the integration for the aromatic ring, and notice that you really can't see it in this form, but the splitting pattern here is very complex. And ordinarily the aromatic hydrogens, the splitting pattern in the benzene ring is more complex than we care to try and get into. That's because long-range coupling is superimposed on next-door coupling. Does that make sense? And that's what tends to make it look much more complicated. So generally, when you have a set of aromatic hydrogens, you just tend to look at the integration and say, oh, there's 5 of them there, or 4 of them, or whatever happens. If there are 5, what does that say about the ring? Well, it is conjugated, but it suggests that there's just one thing attached to the ring. If there's 6, you're talking about benzene. But if there are 5, that means you're talking about a benzene with something attached to it. If there are 4, you've got a di-substituted benzene ring and so forth. So generally, the number of hydrogens appearing under that signal or associated with that signal is real helpful because we know I've got a benzene ring that's got 2 things on it, or 1 thing. Does that make sense? And your structure needs to be consistent with that. The isopropyl group is very characteristic. The isopropyl group, which is this part right here, will have a single hydrogen split into a septet by the 6 neighbors. And here's my septet right here blown up. So I got 1, 2, 3, 4, 5, 6, 7. Then I'll have, in this case, I'll have 3. In this case, I have 3 hydrogens over here because they're next to the carbonyl group, pretty far downfield. But I'll have this great big doublet that represents 6 hydrogens split into 2 by the single hydrogen here. Does that make sense? So this guy will be split into 7 by 6 neighbors. These guys, which are all equivalent to one another, will be split into 2 by that guy. Now, you can see the type B. Are you okay or comfortable with the fact that those are all the same?
Yeah.
There's rotation around this bond here, free rotation, and free rotation here and here, which makes all of those hydrogens experience the same average environment. So all 6 of those are considered equivalent. We're supposed to propose a structure for this spectrum. Okay, and we're given a boost here. We're given a formula, C4H10O, and we're also put at a disadvantage here because the integration line is lost behind a couple of blow-ups here. But I can tell you that this distance right here is twice this and twice one that's hidden right here. Okay, can you see what I'm talking about? So in terms of height, I got 2 to 1 to 1, and I think that looks like about 3 up there. I can probably measure it here. This looks like about a little over 1. This is actually what? 4. looks like. So, or 1, 2, 3, that's about 4. Now, before we worry about the total number of integrations here, let's look at the splitting pattern and see what it suggests to us. What does this great big doublet here suggest to us?
The CH, there's only a CH next to it.
Yeah, there's only one hydrogen next door. It looks like there's a whole bunch of hydrogens that are identical to one another, and there's one hydrogen next door. Does that make sense? And so we're going to have,
CH with a bunch of
and it could be like this. In fact, it could be this isopropyl business we were talking about a moment before. Does that make sense? All right. Then I've got this guy down here, and it looks like it might be about one hydrogen. That could be this guy. Because I know there's only one hydrogen on this carbon, true? Because if the chain goes on, this carbon can only, I mean, based on octet rules and so forth, can only be attached to one hydrogen. So, it's split, not into a septet, but 1, 2, 3, 4, 5, 6, 7, 8, 9, it looks like. It looks like there's how many hydrogens next door?
8.
N plus 1 rule says there need to be 8 next door. Does that make sense? So that suggests that there might be a CH2 over here like this. Because this hydrogen now has 6 neighbors here and 2 neighbors here, which would be 8. Does that make sense? Now I notice from the formula that my structure needs to have an oxygen too. Okay, so what, is there any evidence in there that might suggest an oxygen structure? Yeah, it looks like this singlet right here could be the oxygen, and notice it integrates for maybe one hydrogen like this one did. Okay, so we've got an OH in there somewhere. And we've got, excuse me, 4 carbons. Excuse me. And I've got 3, 6, 7, 9. I've got all of the parts that I need. So what will it look like? Yeah, it looks like we might just pour alcohol here like this, and that looks like that might be a reasonable structure. And notice, because of this alcohol group here, what can I expect about the position of those hydrogens?
Downfield.
They'll be downfield. And notice that those hydrogens would be split into a doublet by this guy. Is this making sense? So that looks like a reasonable hypothesis. When you're doing an NMR, and you each can follow your own strategy, but what I would do, and what I do, is I look at the splitting pattern first. Now, actually, the first thing I look at is how many peaks, so that I know how many kinds of hydrogens are there. Then I look at the splitting pattern, and I start making up subunits that I have to know, that I know have to be there. For example, like great big doublet with a lot of hydrogens, that's kind of diagnostic of a kind of a structural unit that's pretty hard not to recognize. Put all of the structural units that you can see from the splitting pattern down, and then put them together like a puzzle. Okay, it's probably the easiest way to do it. All right.
Where do you see the global scale? This
Well, I was looking at this. This came along here, and at the peak, this jumped about maybe 1.5 units. Here's a unit here. And then up here, this jumped maybe about 3/4 of a unit. Now, in a real spectrum that was actually marked this way, you'd actually get a ruler out and measure the vertical jumps.
Okay, so you're not looking at the total peak height, you're just looking at the jump.
Exactly. This thing isn't integrated. And as it's coming along, it jumps based on the area under the peak. Because notice that if I've got a doublet, the peak height is going to be different than if it were a singlet. A singlet would be taller, but it would have the same area as the doublet. So the integrator actually runs and makes a jump over the course of the peak, proportional to the area under the peak, which is proportional to those hydrogens in there. And so this looks like a CA, this two hydrogens, one hydrogen, and probably four hydrogens up here. So, can you see what I'm talking about? Now, in a number of the spectrum that I've given you, or spectra I've given you, the integration is actually given to you. It would say 5 hydrogen or whatever, but sometimes they're presented in this fashion from some recipes. Okay. Oh, and this goes through what we just went through, coming up with the same structure that we figured out. Now, coupling constants, and I made mention of these, when hydrogens couple with one another and splitting occurs, the distance between the split peaks is what we call a coupling constant. It will be measured in hertz. It's independent of the strength of the applied magnetic field. In other words, the splitting distance in hertz is the same if we're working in a 60 megahertz system or a 300 megahertz system. Okay, and which is nice because that helps us, because a number of the more sophisticated NMR instruments can run in multiple modes. And if I see splitting that looks too complicated for me, I can run the instrument at 300 megahertz rather than 60, and it will expand the scale so that I can see the splitting a little bit better. But that splitting should remain constant, no matter what type of instrument we're using. Now, some approximate coupling constants, they're given the symbol J, by the way. In hertz are shown here. We've got carbon single bonds with hydrogens attached to them, normally about 7 hertz. A pair of hydrogens located on the same side of the double bond, cis, to one another, about 10 hertz. Trans, about 15 hertz. Geminal, same carbon, about 2 hertz. Okay, on aromatic rings, the ortho, or side to side, is about 8 hertz. This is long-range coupling. Notice that we're actually, can you see that that's long-range coupling? And I was talking about that. So if I had some hydrogens that were splitting one another ortho, and the meta coupling was superimposed on that, how would that make it look?
It would be like,
It's a
it's gonna
technical
be 3,
term.
well, it's gonna be is it the combination of both?
It's a combination, the technical term I would use is messy. It would be hard to interpret because you'd have doublets or whatever on top of doublets. Okay, and as a consequence, and we talked about this a moment ago, when we see aromatic hydrogens, because of this effect, very often we don't try and interpret what it means. We just say, oh, there's 5 hydrogens hiding under the signal. For that reason. Now, allylic hydrogens attached to double bonded carbons, their hydrogens will split by about 6 hertz. Now, notice that this is a pretty subtle effect. What kind of an instrument would you need to have in order to actually measure these values? And the answer is expensive. You need at least a 300 megahertz system so that the separations are clean enough and clear enough so you can sit down and using a hertz scale figure out what the separation is or what the scale is. But for those folks that have access to that kind of technology, this can be done. An example, and this is pretty sophisticated, and they don't really give us an analysis here, but this is a nitrotoluene. Toluene is a benzene ring with a methyl group on it, and this is a nitro group. And we've not really discussed benzene rings or nitro groups at all yet, but this thing would have a yellow color, and it has an interesting NMR. Notice down here, it's got a doublet at about, 7.3, and it's got another doublet about 8.1. Okay? And